whatever the code is on the back of your clicker. Registration just associates your name with that code. All right, so let's take a look at the warm-up here. All right, so we start off given a linear system, and we're given a linear system. We want to write the system in as many different forms as we can. So we'll start off by writing it as a vector equation. As a vector equation, this looks like x1 times the column vector 2, 6, plus x2 times the column vector 3, 9, is equal to the column vector 1, 3. So that's us rewriting it as a vector equation. As a matrix equation, it would look like this. It would look like the matrix 2, 3, 6, 9 times the column vector x1, x2 equal to b on the right-hand side here of 1, 3. So that's our AX equals B form. And lastly, as an augmented matrix, we would write it as 2, 3, 1, and 6, 9, 3. So there's my three forms. Any questions about the forms here? All right, number 2 is solve the system. So we're going to use that augmented form. We're going to simplify this. The easiest way for me to do simplification is to take the second row and subtract 3 times the first row. So when I do that, I will get 6 minus 3 times 2. So 6 minus 6 is 0. 9 minus 3 times 3 is also 0. And 3 minus 3 times 1 is also 0. Now I get this as my echelon form, my row echelon form. So I can look at that and see a whole bunch of stuff. What can I see from that row echelon form? Infinitely many solutions. So there are infinitely many solutions. Infinitely. Maybe. Either way. Infinitely many solutions. Because we know that the right-hand column is not a pivot column, is not a pivot. And what does that tell us?
It's consistent.
That it's consistent. There are solutions. You take that thing plus the fact, plus there are free variables. There are free variables. Which one's our free variable? X2, absolutely. So X2 is our free variable. So we do have solutions, and we have a free variable, therefore there's infinitely many solutions. Now to find out what the solutions actually are, we'll take this form. If we want, we can actually finish it up, put it in reduced row echelon forms by dividing the first row by 2. We'll get 1, 3 halves, and 1 half. And then going back to our linear system, we would have x1 plus 3 halves x2 equals 1 half. And we could solve that thing for x1. So that's what x1 is in terms of the free variable. And of course, what's x2? Well, it is the free variable, so that's equal to itself. That's us forming our solution. All right, any questions about this? Any questions from the warm-up? All right. So once again, it's not about just going through and finding the solution. Really, there's a lot of value right here in this discussion. Right, those concepts are very important. Being able to justify those statements is an important part of the process. All right, so for today, first thing I want to do is collect quizzes. So make sure your name's on those and just pass them over here. I also just want to be clear about these quizzes. These are take-home quizzes. I know I really encourage group work and talking and double-checking our work, a lot of stuff we do in class. This is a quiz, though, so future take-home quizzes, it's independent work. I have no problem you guys discussing problems, but we have to distinguish that between working on it together and sharing action. Any questions? All right. So, let's see. Okay, that's collecting the quiz. Next thing up there is register iClickers. That's what we did in the warm-up time, was register our iClickers. I'm going to try to use those kind of now moving forward. I generally don't use grades with those. They're really just something I use to poll the class to make sure we're following the lecture as we go through. So if you don't have yours yet, still on the way or something like that, don't stress out too much about that. So now we're going to take questions on the homework 1.4, or any questions you have for the quiz. I'm happy to work through problems from the quiz as well. After that, we're going to get into section 1.5. So, questions. 7 questions. Yep. Number 9 from the homework. So is this a question from the problem or a question about the entry onto the computer?
The computer.
Okay, absolutely. Let's bring it up there. Okay, so 1.4 homework. And question 9.
Yes.
Okay. Okay. So we have U and V and W. It can be shown that minus 3U minus 4V minus W equals 0. Use this fact and no row operations. Find x1 and x2 that satisfy this equation. Okay. So is the question with this one, or are there more parts to it?
Just that.
This part? Okay. All right, so we have minus 3 times U, minus 4 times V, minus W equals 0. Okay, so what's going on here? We have this equation right here. And how is this thing kind of related to this matrix-looking equation? That's really the question. This matrix equation also looks like a vector equation, right? We can go from a linear system to a vector equation to a matrix equation. And if we took that thing and we wrote it as a vector equation, it would look like this. It would look like x1 times negative 2, 4, 6 plus x2, 3, negative 2, negative 7 is equal to negative 6, negative 4, 10. Okay? That's just us taking this matrix equation and looking at it as a vector equation. Now think about it in terms of a vector equation. And I'll say that this is x1, this looks like u, plus x2, this looks like v, and over here this looks like w, right? And so this almost looks like the equation they gave us. If we just subtract the w to the other side, we would get x1u plus x2v minus w equals this thing. And so what does that tell us about x1 and x2? Negative 3, negative 4. Let's see what's Yeah, does that make sense? So it's really just seeing the relationship between the matrix equation and the vector equation. Okay. Other questions? Any other questions? From the quiz or from the homeworks in the section? All right. Okay, so section 1.5. Right, so there's lots of stuff in the section, as with all these sections. Some of the things that I feel that you should kind of be able to take away from the reading, some of these items, knowing what a homogeneous linear system is, being able to identify those things, being able to explain why every homogeneous system is consistent, and determining if a specific homogeneous system has non-trivial solutions. So these are some of the big ideas from the reading, not some of the details, but the big ideas. Any questions about some of these big ideas? All right, let's take out a piece of paper real quick. We're going to take a quick kind of reading quiz based on those big ideas that we should be able to pull out from that reading, just to make sure that we're preparing for class and doing those readings. All right, so here it is. 4 questions, even though I'm reusing the number 2 apparently. The first 3 are just label the following as homogeneous or non-homogeneous. We have these systems. I think from the reading we should really get that definition down. So just label those systems as homogeneous or non-homogeneous. And number 4 here is explain why every homogeneous system is consistent. So a little statement in words, however you want to answer that. Give you a couple minutes to answer these, and then we'll pair them out. We'll hand them in to make sure your name is on them. All right. Make sure your name is on it. Start passing them over to this side over here. All right, so once again, these quizzes aren't meant to be tedious. They're just meant to be reminders that did we do the reading. I don't want them to be punitive. I want them to be a reward for doing the reading. Nice way to boost your quiz average. As long as you're prepared for class, you should be 100. course, the reason we do the quiz is because I really feel preparing for class, going through that section ahead of the lecture is just a valuable thing. Pre-soaks the brain to this stuff here. All right, so let's go through it real quick. So, homogeneous or non-homogeneous equations. The question is, what really is a homogeneous equation? A homogeneous equation can be written as AX equals 0. That's a homogeneous system. That's it. Right? It can be written as AX equals 0. So here, we have AX equals some other vector, not the 0 vector. So that one is non-homogeneous. The next one over, we have a matrix. We have a vector equal to the 0 vector. That one is homogeneous. And so once we're happy with that definition, these should be pretty quick problems here. The last one does have a 0 on the right-hand side, but is it homogeneous? No, because that one looks like AX minus B equals 0, which is not the same thing. So that one's non-homogeneous. Okay? That's all there is to it. Homogeneous means it can be written as AX equals 0. So then explain why a homogeneous system is consistent. Explain why every equation that looks like this has a solution. Why does it have a solution? Can you think of a solution? Yep.
There can't be a column or a set. They all have to work up to 0.
Sure, absolutely. That's one way you can do it. I would totally accept that as an answer, right? If we have this thing as A augmented with our B thing over here, well, in this case, B is just the 0 vector. So no matter how I add and subtract, no matter how I do row operations on this thing, that will never be a pivot column. So that's totally acceptable as an answer for this one. Here's another one. There's a solution, right? If I take the 0 vector and multiply by this matrix, I'm going to get the 0 vector. So here's a solution no matter what A is. So it's always consistent because there's always this solution. Always X equals 0 is a solution. Okay? Now X equals 0 is kind of a special solution. We're going to call this the trivial solution. That's right, trivial solution. Okay? Because it's trivial to find it, right? It's X equals 0. It's always a solution to these things. You can look at it by inspection and say, yes, the 0 vector is a solution. So really, if we always know that one is a solution, if we always know that our homogeneous system is consistent in this solution, really the question is, are there non-trivial solutions? Solutions that aren't equal to 0? That would be the question. So maybe another question before we dive into that one is, can there be one other non-trivial solution? Could I have the 0 vector and the vector 1, 2, 4, and have those be the only solutions? Would that be possible? What are my options for the solutions to a linear system? Absolutely, I can have 0 solutions, 1 solution, or infinitely many solutions. I can't have 2. I've already eliminated one of those options. There's definitely solutions because 0, 0, 0 is a solution. So if there are any non-trivial solutions, then there are infinitely many solutions. Okay. So if there is one non-trivial solution, then there are infinitely many. Now, what's usually the calling card for infinitely many solutions? If I already know it's consistent, how can I tell if there's infinitely many solutions? What would it have?
Free variable.
Free variables, absolutely. So, when there are infinitely many solutions, there are free variables as well. So that's another way we can think about this, is how do I tell if it has non-trivial solutions? It depends on if it has free variables or not. So now we're going to take out our clickers. We're going to do 2 quick questions here. I'm talking about this homogeneous system, AX equals 0. So the things I have written down here are not augmented matrices. They're just the matrix A. Because it doesn't really pay to write a homogeneous system as an augmented matrix. Why not?
That's zeros in that
I
column.
have zeros on the right-hand column. And it doesn't matter the row operations I do. I'm just going to be moving around a bunch of zeros, right? So that doesn't make sense for us even to write that down. I'm just writing the matrix A for this homogeneous system. So the question now is, do these things have non-trivial solutions? So for this one, right, A says, yes, there are non-trivial solutions. And B says, no, there are not trivial solutions, non-trivial solutions. I'm going to start my clicker thing going, and you can go ahead and answer one of those. So yes for non-trivial solutions, or no for non-trivial solutions. And we got in here about 6, 12, 18, 24-ish. I'm sure some people don't have clickers here today, so 20 sounds about good. Let's take a look now. We're pretty mixed on whether this one has trivial solutions or not. All right, how do we tell? Well, if I have this matrix thing, I can put it into a row reduced form to see if it has free variables or not. So I'm going to do a row operation on this thing. I'm going to leave that first one the same, leave the second one the same. I'm going to eliminate this value. I'll take row 3 minus row 1. I'll get 0, 0, negative 1. And once again, I could certainly write down the augmented system. I just don't need to because it's just all zeros. But it's important when I'm looking at this final thing to say, wait a second, this is not that right-hand side. Right, so I can't look at this and say, oh, look, the right-hand side is a pivot column. Well, no, it's not, because I just haven't written down the far right column. Okay? So I'm looking at this. I say, wait a second, this has a pivot position for every row. Right, if I added my thing of zeros over here, this would say x3 is 0, x2 is 0, and x1 is 0. And I can finish this by eliminating this term if I want, but I really don't need to. In this form, I can see that I have a pivot position for every row. So that means this thing has a unique solution. There are no free variables. Okay? So that means there are no non-trivial solutions. So this one is B. Questions about that? All right, I'm going to stop this one. And I'm going to start the next one. So for this next one, now we're working on this one. Are there non-trivial solutions? A for yes, there are non-trivial solutions, and B for no, there are not non-trivial solutions. Only x equals 0. And C means I don't know. And I actually encourage you to put C if you don't know. Because I'm using this clicker just to see how fast or slow I should go through the lesson. So if you don't know, don't guess to try to get it right, because that means I'll skip the topic, right? So if you don't know, put I don't know, and I'll talk about it more as I go through it. Okay, so I got my 19. Let's take a look. Pretty happy. 14, 1, and 4. Okay, so we have the majority of people are saying that yes, it does have non-trivial solutions. Once again, the idea, how do we test, is to say, okay, there are going to be non-trivial solutions if there are free variables. So what I need to do is row reduce this thing to see if there are any free variables. So I'll do my row reduction. In this case, I am just going to say row 3 minus 2 times row 1. And R3 is going to be equal to R3 minus 2 times R1. That's the row operation. When I do that, I will get 2 minus 2 is 0, 0 minus 0 is 0, and 2 minus 2 is 0. And when I look at that REF form, are there any free variables here? What's my free variable? x3. x3 is my free variable over here. So there are free variables. I already know it's consistent because it's homogeneous. So therefore, there are non-trivial solutions. So this one would be A. Yes, there are non-trivial solutions. All right, any questions about this one? Remember, make sure you get your questions answered. It's your grade. If you have questions, make sure you ask them. Okay. All right, so the big summary here. AX equals 0 has non-trivial solutions. Once again, this thing here is if and only if. Sometimes it's written as IFF. If and only if the system has at least one free variable. So once again, what are these free variables? We've talked about them in terms of independent variables. These are the ones we can choose their values to find more specific solutions. You can think about them in terms of parameters. If you've worked with parameters before, they're the things that we can wiggle in our solution. So one of the other topics for this section is to write our solutions in parametric form. So the idea is these free variables are basically our parameters, and writing a solution in parametric form just means to express the solution in terms of its parameters. So here's an example of me expressing it in terms of its parameters. The reason I write it like this, x is some value, some parameter, some variable here times a vector plus this other value times a vector, is because it's easy for me to generate specific solutions. Right, this is all buried into equations. I say, well, if x1 or x2 is 1, then I have to put it here, here, and here, and kind of mess with it a bunch of times. But if it's in this form, I just put a 1 there and a 2 there, and I add them up. It's much easier to generate our solutions when we have them written in this parametric form. So that's an example of writing in parametric form. Your book will write it as, let's see, solution looks like SU plus TV. That's how they actually write it in the book as the definition of parametric form. Right, but it's just the names are changed to protect the innocent, right? So all they're doing is they're just changing the names. I say x2, they say that value be s. x3, they're calling it t. These are just some random vectors, specifically these vectors. So they're just changing the letter names. So don't let that confuse you. Yeah?
Just a question for those then. So if we left it as x1, x2, that's going to be okay?
Nope, absolutely. You can leave it as x1, x2. I'm not too picky about that. I mean, the reason they change it is because x1 officially means the first component, right? And so it's kind of has that placeholder. Right? But I think it's really a natural thing when we write out our solutions in terms of x1 and 2 to factor them out and kind of see those are parameters. But once we see that formally, we should say, let this be the parameter s. All right, but I'm not too concerned with that. Okay, so let's look at what we had there. All right, so this is that last problem we went through. We said that there were free variables, so there were non-trivial solutions to that homogeneous system. All right, we reduced it down to this form. And so for me to write out the solutions, I could say there are the solutions. All right, I went back to my linear system to write those things. Now really when I write my solution, I want to write it as an x1, an x2, an x3 in terms of all the variables. Say, what are each of those values? Well, x1 I can express in terms of the free variable. x1 is now just equal to negative x3. x2 has a clearly defined value. It's equal to 0. And x3 is my free variable. So I'm just going to say, well, it's equal to whatever it is, whatever we're calling it. And here, once again, if you wanted to formally say, let x3 be a free variable, I will call it s. Feel free to put in an s there. Okay. Now I want to write this solution, though, in parametric form. Here's my solution as a vector. When so I'm writing ax equals 0 vector. This is my solution as an x I can plug in here to get a true statement. What that x is, it has the components x1, x2, x3. But now I have values for those things. x1 is negative x3. x2 is 0. x3 is x3. So this is my solution vector. Now I wrote that solution in terms of its free variables. So what I can do is I can pull out that x3 value, my parameter value. And that's the form I want to write it in, as a sum number times a vector. I'm pulling out my free variable, and the result will be negative 1, 0, 1. So make sure if you have questions, so I'm going from here to here, you ask. Are there any questions about that? Does that make sense, pulling out that value? So that's our solution. That's our solution in parametric form. It's really just some number times this vector. And I like that form because I can say, what are solutions to the system? Well, negative 1, 0, 1, negative 2, 0, 2, negative 3, 0, 3. It's very easy for me to list a whole bunch of solutions. I can really feel what that solution looks like. Any questions about that? Other ways you might see it written are, okay, I don't want to use x3, I'll use some parameter. So s times negative 1, 0, 1. But then I have to say what s is. So I might say for all s in the real numbers. That's the crazy, fancy math notation. Right? So I'll use a little bit about this. Don't worry, I won't expect you to know all this. But it's good for you to see a little bit now because you'll see it in later classes. Upside down A just means for all. So for any s that belongs to the set of real numbers. Once again, I'm not going to put that on quizzes or tests or anything like that, but it's good for you to see it as you go through because eventually you hit a class and they'll just somehow expect you to know all that. So. Okay, so now what is this solution? I said it's a number times a vector. What is that graphically? So what does my solution look like if you plotted it? What would that look like? It would look like a line, absolutely. So what is this thing? What is the geometric representation of the solution? It's a line. Why is it a line? How do we know it's a line? Well, we have a whole bunch of ways to justify that the solution is a line. One, because it's a linear function of one independent variable. That's why. Because I have one free variable, one parameter value. So what's a linear function of one independent variable? It's a line. Functions of one independent variable in general are just curves. Right? Y equals x squared is a function of one independent variable. So we need a linear function of one independent variable, so that's a line. How about because the equations tell us it's a line? Remember our equations were this thing. Those look like lines. Right, this thing, if I just change it to y and x instead of x1 plus x3, that really is the equation for a line. And so because the equations tell us that it's a line. Why else? What about the original system? If we look at what this linear system was originally giving us, it was giving us x1 plus 0x2 plus x3 equals 0. That's actually the equation of a plane. And the next one would also be equation of a plane. And the third one would also be an equation of a plane. But it turns out the first plane, x1 plus x3 equals 0, and the last plane, 2x1 plus 2x3 equals 0. I just multiplied that by a number. That's actually the same plane. A solution is basically where these three things intersect. So essentially I have two planes, right, because these two are the same plane. And so where are they going to intersect? At a line. Right, so these two planes, if they intersect, are going to intersect at a line. That's another way I can see my solution should be a line. Because these planes intersect at a line. So really, a solution to a linear system is the intersection of all the objects. All right. And why else? Because our solution is s times this vector, negative 1, 0, 1. So what does that look like? Let me draw my three-dimensional coordinate system. x1, x2, x3. Right? Let's find one solution. If s equals 1, then my solution is -1, 0 in the x2 direction, and 1 in the x3 direction. My solution is that point. What if S is 2? Well, then my solution is this point. What if S is 3? Well, then my solution is this point. What if it's -1? Then it's down here somewhere. Right? So that number times that vector is just a scaling of that vector. So our solutions are that line. Okay, a lot of justification there. Any questions? Any questions about the graphical representation of the solution? Let's see, let me go back up real quick. What if there was two free variables? What if my solution looked like S times -1, 0, 1 plus T times 2, 1, 1? What if that was my solution? How would that look like? It would be a plane, absolutely. Because it says two free variables. So I'm looking for a linear function of two independent variables. If I have two independent variables, those are surfaces, and a linear surface is going to be a plane. Another reason I can see that is because if I really plotted that thing, I'd be having this whole line just like I had before, but at any point I can also add some value here. So I could take this point and add maybe 1 times my vector. I'd be adding 2, 1, 1, adding 2 in this direction, 1 in this direction, 1 up. I'd be adding this vector, but I could also add 2 times that vector or 3 times that vector. Right, so I could get to any spot on that line, or this line, or this line. So I'm getting any value in that plane. Okay. Now what about the intersection? Well, if I was in this case, I would have my 3 planes. And if I have my 3 planes and say, how do these things intersect? They could not intersect at all. Like this, that would be no solutions. They could intersect at exactly 1 point. If I went like this and like this, now the intersection is just this little corner spot. That would be 1 solution. I could have a case where I have 2 of the same planes, and like this, infinitely many solutions, and it's a line. Or I could have this. They're all essentially multiples of each other. They're all basically the same plane, in which case the solutions are anything on the plane. So those are those 3 cases geometrically. Any questions about that? Okay, so these are all our solutions. What's the value when S equals 0? What's the solution when S equals 0?
0.
0, right? It's the 0 vector. It's the vector 0, 0, 0. That solution is this thing. But I already knew that was there. I already knew that was going to be in my solution space here, in my solution set. Why is that? Because it was homogeneous, right? So I knew that solution right from the start. But of course, I can also see it in that parametric form as well. Okay. Now what about a non-homogeneous solution? Go ahead and solve this linear system. Find the solution here. And write your solution in parametric form. Go ahead on paper, solve this system, and write your solution in parametric form. I gotta stop using my notes for planes. It just messes up the order of my notes. Okay, I got started here. See, a lot of people getting started, doing their row reduction, writing out some equations. It's like some people are getting stuck on their parametric form here. So I took my linear system, I rewrote it as a linear system, and now I'm just writing x1 is equal to this, x2 is equal to this, x3 is equal to this, using my free variable. Now I got to write in that parametric form. And this one's a little weird because I have this constant here. I actually can't factor just an x3 right out of this thing. But what I can do is write it as the sum of two vectors. My constant vectors plus all the stuff that have the x3s in it. And then I can write it as 1, 0, 0 plus x3 times negative 1, 0, 1. And so that would be the parametric form of this solution. I have some regular vector, I'm going to call it p, plus my parameter here, s, and my other vector, I'll call it v, because that's what the book does. That's what this solution looks like. But that solution looks pretty familiar. What was the solution to the last one we did? A homogeneous system? I mean, the matrix was the same over here. When it was homogeneous, what did my solution look like? What was the solution for the homogeneous system? Read it out. Somebody read out the solution to the last problem we just did. What was it?
S. So negative 1, 0, 1.
Absolutely. It was some parameter times negative 1, 0, 1. It's this piece. This piece was the solution of the homogeneous system. So really the only difference is this extra piece here. Right? So it's no coincidence that this happens like this. The homogeneous system is very much related to this non-homogeneous system. Right? So it's not a coincidence they both contain this extra piece here. So why? Why does that work out? Well, let's talk about it graphically. Graphically. What's the difference between that set of equations and this set of equations? We'll look at the first one. Up here, the first equation is x1 plus x3 equals 1. Down here, it's x1 plus x3 equals 0. If those are both planes, what's the difference between those two planes? What happens if I take a function and then I add 1 to it? How do I move the function? I just shift it up 1. When I add just a number to a function, all it is a vertical shift, right? This is our function transformations from Calc 1, right? From pre-calc even. Right, we're just doing a function transformation here. So we have a plane, and now we've shifted our plane up by 1. And that's all we're doing. When we're adding this non-homogeneous piece, we're just adding specific numbers to the equations. All we're doing is shifting those planes a little bit. So it's no surprise that our solution is just a shifted form of the old solution. Here's our regular solution, and we're adding some constant to it. It's just a shifted version. So graphically, right, this solution is just a shifted form of the solution. We did the plot of our last solution. It was this thing. Right, it was that line. But what's our new solution? Well, we have 1, 0, 0. That's this vector. That brings us right to this spot. and then plus any multiple of this vector. So if x3 is 1, I would go, let me change my color here. I go from this vector plus negative 1, 0, 1, so that would be negative 1 and 1. I'd be like this. I'd be at that point.
You have to change color.
You can't really see it on either of these because, anyway. So I have this one plus brings me this spot. If I take a different multiple of that vector, I get this spot or this spot. I get this line is swing up and down like this. So instead of this line, I have this shifted line. It's shifted over by that 1, 0. Okay, now I'm losing it all. Oh, there we go. It's my fault. I wiggled out my cord here. There we go. So I have a shifted version of the other solution. Now, how else can we see the solution? This solution is just, it's parallel to my old solution. I just took this line and shifted it up. So it's actually in the same direction as this thing. What's the direction it's in? It's in the direction of V. It's in the direction of V, but instead of going through the origin, through the point 0, 0, 0, it goes through the point P. All right, so now our new solution just goes to the point P, but it's parallel to V. It's parallel to our homogeneous solution. Okay. Now for the big theorem. Okay, given that AX equals B is a consistent system, there are solutions, and that P, here's P, is a solution. P is a solution to this thing. That's what we're saying here. If P is a solution to the non-homogeneous thing, this is one specific solution, by the way. This is the 1, 2, 4. Any solution that works. If this is any solution that works, then the solution set, right, the set of all the possible solutions, is just P, the one solution we did have, plus this other solution where this is any solution from the homogeneous system. Okay. So this is how we form a family of solutions. A lot of times it's much easier to solve this one. And this is actually really applicable to differential equations, because it turns out you can write a lot of your differential equations in terms of linear systems. So what we do is we take a hard differential equation, we change it to this homogeneous thing. We say, okay, let's find this solution. We find this one. And then all we have to do is find one solution for this. And then the family of all solutions is just our one solution plus this group of solutions. And so that's the plan here. That's the big idea. Okay, so what we saw up here was we had the solution from the homogeneous equation. And really, I didn't have to go through this whole solution process here. All I had to do was find out one value that would work, and I could have just constructed this full solution here. Okay, second justification. This is more of a formal proof for this thing. And it's good to see these style of proofs because they're very common in linear algebra. So don't worry so much about the details here, think more of the structure. Okay, if this thing is a solution to the non-homogeneous equation, and V sub h is a solution to the homogeneous equation, I want to show that this thing is a solution to the non-homogeneous equation. I want to show that if I can add them together, it does satisfy the homogeneous equation. So how do I show that this is a solution to this? How do I show that something's a solution of a linear equation? If I have 2x equals 6, I said, is 3 a solution? How would you prove it to me? I'd put it in there and see if it makes a true statement. Same thing here. So I got to take this thing, P plus VH, plug it in, do some stuff, and hope I get out to B. If I get to B, then yes, it's a solution. So I use some properties. If I take a matrix times the sum of some vectors, I can use the distributive property to say that it's equal to this thing. But then I say, wait a second. What is this thing? What is V sub h? It's the solution to the homogeneous equation, which means that if I take A times V sub H, what should I get? 0 vector. So this thing is just the 0 vector. So now I have A times this thing equals, or plus the 0 vector. But what is P? P is some solution from the non-homogeneous equation. So when I plug in P into AX, what should I get? B. So now I have B plus 0. Well, B plus 0 is just B. So I've shown that when I plug it in, I get to just B. Therefore, I've shown that it is a solution of the non-homogeneous equation. That's really what the proof looks like. The important thing is to understand that if I say, hey, this is a solution to the homogeneous equation, it means that A times this thing gets me 0. That kind of definition of a solution. We're actually using that in a proof. All right, so the last thing I was going to do is I was going to solve this thing. Going through all the mechanics, we would find a solution that looks like this. 7, negative 1, 0, plus x3, 1, 1, 1. All right, we've done the row reduction. If this is the solution to this non-homogeneous system, what would be the solution to this system? Same thing but homogeneous? What's the solution to this one? Absolutely. The solution to this one is just this piece. So we wouldn't have to resolve this one, it would just be that piece. Okay, that's all I got for today. For the next time, we're going to cover 1.7 because we're not officially doing 1.6. I would highly encourage you to read through 1.6. It's just applications. There's some from economics, there's some from chemistry. You don't have to read through the whole section. Right, but if you're working in chemistry, read that application. Or if you have an economics background, read that one. So just kind of browse through it real quick. Do a quick reading because it's useful. All right, and office hours are right now.
No, I actually just moved in and I figured out that 4 hours a day, 4 days a week, for 8 weeks, I can be in this room for 128 hours.
Probably
No, I got an hour.
that one. That's
Mental analysis. Yeah, I can do mental analysis.